Okay, thanks, Giovanni. Thanks, the organizers and everybody. I want to talk about a recent work I did together with colleagues, well, two colleagues at the University of Pisa, Paolini and Tortorelli, and Evgeny Stepanov, which is almost a colleague in the sense that he's visiting Pisa more or less every year for a few months. And okay, the subject is the isoperimetric clusters. We looked at a specific question, but in fact, let me just give a brief introduction to this problem, which is one of the classical problems in the calculus of variations. So probably all of you know, but let me just go through. So what is the problem? Okay, so the variational problem is just to minimize, to find, so it's not an evolution problem, but so given a set of volumes, M1 and Mn, these are volumes, so constants, which means that Mi is just 0 plus infinity. We want to find the minimizer, a cluster. So let me just draw a picture. Well, E1, E2, En. We look for a minimizer of the perimeter of n chambers, and with the assumption, with the condition that each chamber has volume Mi. So if you want to write, it's just the sum minimizer of the sum of P of each the perimeter. Sometimes you can put here 1/2 maybe, I from 1 to n, plus the perimeter of the union of EI, because essentially, and then maybe you can divide by 2, this here, with the condition that each, okay, EI are disjoint, of course, are disjoint, let me say like that, and the measure of each EI is equal to Mi. So that's the problem. Basically, you want to find a set of n disjoint chambers such that the sum of all the interfacial energies is minimized. I put here the union here is needed because if not, you want to count every interface exactly once. Okay, and okay, for simplicity, let me just introduce let me just call that E will be for me that's the set of all the chambers EI, and M will be the vector of the volumes M1, Mn, and this here will be called just for simplicity the perimeter of the cluster. So in this sense, we are minimizing the perimeter under this condition here. Okay, of course, as a remark, which is obvious, when n is equal to 1, this is a well-known isoperimetric problem, and the minimizer is a ball. Minimizer is a ball, and there has been a lot of works about this isoperimetric cluster problem, but not, in fact, not many issues such as, for example, the regularity in general, the optimal regularity, and in particular the shape of the minimizers are still open and unknown, because of course as soon as you add many chambers, the problem becomes complicated and the shape become very different. There are then also variants I will discuss maybe later of infinitely many chambers, but let me do not enter. Okay, just as a quick overview of the results, when n is equal to also is established, and essentially here is a double, how do you say, double ball, in the sense that with two chambers is known, and then the minimizer is just 2 balls, even in Rn. Okay, here we are, let's say in Rd, that we are in Rd, where D is a general dimension. Okay, the problem becomes already significant in R2, but we can cast a problem in Rd. And when n equal 2 is a double ball, but this was already quite difficult and more recent, and in fact a complete. Now I don't remember precisely all the literature, but a complete answer when n equal 2 is due to Hutchings, Morgan, Ross, Ritoré, Ross, and then extended later in every dimension. And also some results are known about the precise shape. Some results are known in dimension 2. So in this case, when D is equal to, okay, when D is equal to, there is also a result by a few authors, now I don't precisely, about n equal 3. And here is exactly the triple, how do you say, triple ball? Triple bubble. In fact, it's usually called double bubble, triple bubble. Triple, where you have essentially 3 circles and of course of the right volumes. And here you can also have arcs of circles, and something also when n equal 4 and all the volumes are equal. So EI equal EJ, and here you have a quadruple bubble which has a specific shape. I think something, if I well remember, something like that. But only with, for n equal 4, only with, this was a result. Okay, here I don't remember, there are a couple of results in this triple bubble case, and here for n equal 4 was a result by, recent result by, I think, Paolini and Tortorelli, this co-authors. Well, in fact, there was a previous paper by Paolini and Tamanini, and then Paolini and Tortorelli. And something else, when D equal to, the shape, the regularity is more or less well known, because every minimizer for every number of chambers and every volumes is just made by a connected union of arcs of circles. So they say there is a complete regularity here, complete regularity. I don't know, the first who precisely wrote maybe is more Frank Morgan, and essentially is a set of arcs of circles with different curvatures meeting only at triple junctions at 120 degrees, and a connected. So you have a connected set of circles meeting at a certain finite number of triple junctions. Then, of course, so here at least the existence and regularity part is well established in dimension 2, and the real problem is understanding the shapes, the symmetries. Okay, so essentially the first results about about this problem, there is essentially due to Almgren and this group, and in particular, let me just mention in his group in particular the work by Gene Taylor and Frank Morgan. And there is a very general existence result and partial regularity result, which holds for in every dimension and in for every number of chambers, which is, I think, it's an important result in the theory. And essentially is that for every set of volumes M, there exists always, at least, maybe it's not unique, but there exists a minimizer. And there is, which is bounded, and it's either regular out of a singular set, is regular, where regular here, of course, means once you are regular, so once is locally, let's say, graph of a function, then you are also analytic, because these are constant mean curvature surfaces. So regular means analytic out of a singular set of 0, or out of a singular set singular set of 0 HD minus 1 measure, closed, out of a closed singular set. Of course, as a remark, a complete the singular set is characterized in the sense that is well understood the shape of the singular set only in dimension 2, as I said before, and 3. Let's say the singular set is completely understood, let's say. But I think already in dimension 4, there are some results, and here are results which I said by Taylor and Morgan. Let me just do not enter here, but in dimension 2, the singular set is just a finite number of triple junctions at 120 degrees. And in dimension 3, there is slightly something more because you have lines of triple junctions. So just an analytic line where three surfaces meet at 120 degrees, or you can have isolated points in a finite number of isolated points of which are cones over a tetrahedron. So which means that where six surfaces meet with equal angles. There are some results by White, and then maybe also more recent results by Colombo, De Filippis, where there is an analysis of the singular set in general, but a complete classification of the singular set is still not missing. Is still missing. Okay, so let me just tell you what is a possible strategy briefly of the proof, because I will. Of this theorem. So essentially this one is the theorem of Armageddon has two parts. One is existence, so it's essentially a compactness. And the second part is regularity, where in the regularity part, of course, I also include boundedness, because boundedness is a sort of a weak, but it's a basic regularity step. So let me just mention briefly the existence, the strategy for existence. I would say let me just, by now it's standard in some sense, but at the time was an interesting, I would say, idea. Let me just mention in a very simple case, even if of course it's more interesting for clusters, but let me just mention the strategy when we have only one chamber. So for the isoperimetric problem, of course, in that specific case, you could directly argue that the minimizer is a ball by comparison, but let's just for simplicity fix n equal 1, which is just one phase. And so essentially it's based, and let me just, there are little variants for this existence part. Let me just follow the concentration compactness strategy. So essentially you need, what is the problem is that you start from a minimizing sequence, EK, minimizing sequence for the perimeter, and of course, which means that EK has fixed volume for all K, and then you want to pass to the limit in the minimizing sequence using the semi-continuity of the perimeter. The problem is that RD is not compact, and therefore you can lose some mass at plus infinity, and then in the end you will find a minimizer, but you can lose the volume constraint. So essentially, the point is to use a compactness theorem in RD for the perimeter, basically. Let me just if I have a set, if the perimeter of a sequence of sets is bounded and the volume of the sets are all equal to M, in fact, maybe an inequality from below would be enough, then in fact, this family of sets enjoy, in fact, a compactness property once you sort of compactify RD. if you compactify RD in some sense, or if you relax your problem, then this one is a compact family, and so you can just, because then you can say that, okay, you can lose parts at infinity, but you can follow each parts, and in the limit, you end up not maybe with a single set, but with a family of sets which solve a suitable relaxation of your problem. In this case, the problem with one phase is very simple, it's just a perimeter, a suitable relaxation of the perimeter. So let me just say what happens then. There exist translations, so ZKI in RD, these are translations of your set, such that the family of translations are independent, ZKI minus ZKJ go as k goes to plus infinity to plus infinity, if I is different from J, and EK, your set translated with my set of translations will converge in L1 to a limit set EI. For each I, here I is in N. And so, and the sum of your parts is equal to M. So you have to think basically that your set splits in a possibly countable number of components, but these components are your minimizer in some sense, because they do minimize perimeter and they still keep all the volume. So in some sense, the family, so let me just change page.
Matteo, the convergence is in L1 log?
Now here is really in L1, because essentially you are already keeping all the parts. You are following one single part, and so you don't lose anymore here. No, you are following one piece, and so you see all the piece. No, sorry, the convergence is in L1 log. Yes, of course, because you are looking at a specific piece. Yes, right. Thanks. So in some sense, you can say that the set EI is a minimizer. In some sense, is a generalized minimizer. It is a minimizer of the relaxed problem. It's a minimizer of a problem which is rather the sum of the perimeter of, how do you say, the sum of the perimeter of EI under the constraint that the sum of the volumes is equal to M. So this is just, how do you say, it's a relaxation, if you want, of your problem, when you have all the parts at plus infinity. Now, okay, in this way, you find not a minimizer of the original problem. Now how do you conclude? How do you get the theorem? Now you need some minimal regularity result in order to conclude, because, and then as a remark, which is important, each piece, EI, is a minimizer. This comes for free by this compactness of the perimeter with volume, with its volume. So each piece is a minimizer. Of course, a piece has less volume, but it's a minimizer with its own volume. Now, how do you conclude? You conclude by some regularity result. If you can show that minimizers are bounded, then you get a minimizer of the original problem. And that's essentially the second point. So there is a general compactness result for the perimeter in some sense, but then you need something, because you want to bring back pieces from infinity in RD, but to be able to do this, you need to know that they are not too spread. You need some regularity, even minimal regularity, and then you get a minimizer of the original problem. minimizer. And here, of course, there are techniques to show that the diameter is bounded. Typically, the two basic regularity results are density estimates or bounded estimate, and they are done in a similar way. In fact, density estimate do imply diameter estimate. And okay, there is here there is a regularity point. And for minimizers of the perimeter, you can show, in fact, both density estimates and diameter estimates. And so, in fact, you get, of course, okay, so the same approach with some little technical effort, the same approach works for clusters, because you see, it's more or less the same thing. If you have not only one chamber, but a finite number of chambers, you follow each chambers. And so the same approach, so the same method works for all n. Okay, now a little remark about this fact that a little observation here is that density and diameter estimates for clusters are more difficult than. So while the compactness part, it's all the same, it's the same, diameter estimate for minimizers is more difficult for clusters. Now, let me just briefly mention why, because the diameter estimate essentially is done like that, essentially. Let me just do an example. It's very similar to density estimates, but it's like that. You have a set, a minimizer. You don't know that the diameter is bounded or not, but you cut with a very big ball. In case of density estimate, you cut with a very small ball is not important, because in some sense, diameter and density are very similar. And of course, you had the minimizer, so what you get in principle should have a bigger volume, but you have a volume constraint minimizer. So if you cut, you cannot directly compare. You cut with a ball, and the procedure is just a cut and rescale procedure. So you cut with the ball, you rescale, you compare the perimeter because you had the minimizer, and you get an OD, essentially, which gives you that either you have density estimate or you have a diameter estimate. So it's in some sense, it's a simple idea. Now, what is the problem for clusters? That once you cut, if you have a cluster here, so a cluster of different parts, once you cut, you're not cutting all the chambers by the same amount, so you cannot rescale. So the cutting is okay, but the rescaling you cannot do in the same way. And as a consequence here, for clusters, you need a more clever idea, no rescale. And in fact, here there is a suitable diffeomorphism done in a way to restore all the volumes, because you need all the right volumes in order to compare. And that's a difficult, which is called Almgren's lemma. And you see, that is a technical issue in some sense, which makes this final part of the diameter estimate, which is needed to have a real minimizer, not in some sense a generalized minimizer. This requires a technical point, which is this Almgren lemma, which is just substituting the rescaling procedure with a suitable diffeomorphism thing. Okay, so let me just add a couple of remarks about this diameter thing. In fact, first remark that in fact in dimension 2, when D is equal to, there is not the issue because the perimeter controls automatically the diameter. So the diameter bound is automatic by the perimeter. So in dimension 2, you have the diameter of your cluster is bounded by 1/2 the perimeter of the cluster. Here the perimeter, I mean the sum of all the perimeters as I defined before. Essentially because in dimension 2, if E is connected, let's say, so the boundary connected, you have this bound here, essentially because you see, because the perimeter diameter, of course, is bounded by, by the perimeter itself. And so in some sense, in dimension 2, the existence becomes easy because you get the generalized, each piece is bounded, and then you bring all the pieces together, and you find that you always have a minimizer. And second remark, the diameter bound in the Almgren work, the diameter bound is not uniform. In the sense that it depends on the minimizer, because if you look inside that Almgren lemma, the diffeomorphism is constructed starting from the minimizer itself. It's not uniform, but depends on the minimizer. Now, it can be made uniform if you fix your volumes. It can be made uniform by if you want, by a compactness argument. That if there is a way to, but in a very implicit way. So in fact, is it true that every minimizer has a diameter bound which depends only on the volumes? Because you can argue by contradiction, and at the end, since the minimizers are a compact class, you can show essentially, but in this way you don't find an explicit bound. So what is important that here, I would say is important, uniform explicit bounds are missing. Uniform and explicit bounds, like the one you have in 2D, for example, are missing for the minimizers. And this will be that here, if you want, you can just say what is a possible conjecture one could imagine by thinking that instead of, by looking at each chamber separately, that one could expect, but I have no idea if it's true, that for a minimizer, some bound of this form could be true, each volume to the 1 over D. But I'm not sure. And this, in the sense that it is, of course, volume to the 1 over D, it would be the radius of a ball of that volume. You sum all the possible, and it would be interesting and useful to have this type of explicit uniform bounds, but these are not, except in the 2D case, are not, okay. And then coming to what we did, we wanted to look at a slight generalization of this problem. So the case, we look at the case of infinite volumes, n equal plus infinity, with the condition that the sum of there exists at least one candidate with finite perimeter. So with the condition that the volumes to the D minus 1 over D is less than plus infinity. So we look at clusters made of many little, but with the condition that at least you have a candidate made by a sequence of balls a sequence of balls of that volume, and that perimeter is fine. So under this condition, essentially with a little technicality, in fact, there is not a big deal, but the compactness result or holds the one I was saying before. So under this condition, there is, as a result, a theorem that there exists, let me just call it, just a moment here. There exists for every set of volumes, infinite sequence of volumes, there exists, let me call it a generalized minimizer, which is a set of EI, and each EI is a cluster. So I don't have a minimal cluster, but I have a set of possibly countable minimal clusters, each one with possibly infinitely many chambers, and each EI cluster minimizing. And each piece at infinity is a cluster minimizing the perimeter with its own volume, which can be minimizing with, let's say, mi less than or equal to m. Mi. These m are vectors now, but let me just use with a little abuse of notation. I'm saying here that each component is smaller than the one. And also, when d equal 2, if d equal 2, since you still have the diameter bound I was saying before is uniform, is independent of the number of chambers in 2D, because it's just the diameter is controlled by the perimeter. Okay, there exists a minimizer. And what we do not have, and so in general, the remark, we don't have any regularity at the moment, so no density estimate. And so as a consequence, no diameter bound in dimension d greater than 2. And as a consequence, no existence of a real minimizer for the moment existence. But in dimension 2, we have existence. But, and we have a very weak regularity. In dimension, we have a very weak regularity in dimension 2. So concerning the regularity, d equal 2, in the sense that, let me just mention, so if you write, if you look, okay, you have how do you show the regularity in dimension 2? You have your set of volumes, M1, Mk. You fix a truncation, Mn. Truncation, you stop at n, M1, Mn, truncation. You have your cluster En is a minimizer with n chambers with Mn as a volume. So you just forget all the chambers which are very small after a given number. And then you want to pass to the limit and to reconstruct your minimizer in the limit as limit of this En. You can do, because in fact, you have uniform diameter bounds, everything works, and semi-continuity of the perimeter. But now you observe that the boundary of En is very regular, it's a bunch of circles, pieces of circles. In some sense, it's regular, and in fact, what you have is that is connected, compact, and H1 of the boundary of En is equal to the perimeter. So in particular, it's uniformly bounded. Now in 2D, in 2D, this class of objects is compact. So connected sets, which are rectifiable also, which H1 bounded and compact are a compact class. So in some sense, you have that, in some sense that your En goes to your limit minimizer in L1, let's say. But the boundaries of En go, let's say, in the Hausdorff distance, because the compactness for compact sets you have in the Hausdorff distance, to some gamma, and gamma is in the same class, compact connected with H1 of gamma less than C. And then you have also that the boundary of V, okay, here I should specify what is a boundary. The boundary is a measure theoretic boundary. So you need to take the points where you don't see, where you are not always inside the chamber or outside every chamber in some sense for all radii. So there is a measure theoretic definition, but this is contained in gamma. So as a consequence, in dimension 2, you have a minimal regularity, very weak regularity. So you know that the boundary, the measure theoretic boundary is rectifiable with bounded H1 measure. Okay, it's not a lot, but for example, it's not very bad. It's not positive measure boundary. But apart from that, we don't know much. We don't know much, in particular because we don't know. So that's already, let me just point out because it's a minimum. What we do not know, and then just I want to conclude with a couple of examples. We do not know where do infinitely many chambers accumulate. So in order to be able to give a real regularity result, we would like to say that the points where you have accumulation of infinitely many chambers are, for example, H1 small, are small, 0 even. Because then outside, well, outside you have finitely many chambers, you already have all the regularity you want. So essentially the issue here is that we cannot control the accumulation of infinitely many chambers at the moment, at least. We have this very weak regularity result. Okay, now I don't want to be too late, just make a remark and a couple of examples. Remark, of course, everything is very stable here because we don't have very refined regularity results. So everything works. Everything works for an isotropic perimeter, of course. Phi of nu. In fact, you could also so P phi of E. You could also put different anisotropies if you want on the chambers, but essentially you can work in an isotropic setting because the compactness is phi is a norm. Phi is a norm on RD. And as we don't have many examples, in fact, and why I introduced this remark, because the only example we have is for a very specific anisotropic case, that's why. So as an example, but the only example, it's easy if you take phi of x, which is a crystalline norm. And so in particular, the isoperimetric set is a square. That's the isoperimetric, the minimizer with n equal 1 set. It's what is usually called the Wool shape for this. Then, of course, if you for some choices of volumes, not all, but for a few, you could divide the square into little squares. For example, let me just give you a specific example. M1, M2, M3 are all equal to, I don't know, 1/4 or whatever. Then I do that. Okay, here I construct a sequence of examples, and if you look, each chamber is a square, and the union is a square. And so, of course, this is a minimizer, because because I'm minimizing the sum of perimeters. If for each volume I already have the optimal shape, which is in this case the square, and this one is a specific. You can do other examples which are similar to this, but it's a very specific. And as a remark, it doesn't work. It doesn't work for the usual perimeter. For the isotropic perimeter, because if you try to do the same example for the isotropic, we tried, but how would you like to do? Well, you fix a circle. It's this Apollonian construction of packing circle. You pack a circle with circles if you want to reproduce the same example. And if you do, you can do, of course, packing circle. Now, okay, the picture is not very nice, but you can do. But you see that somehow the packing is much worse because a circle is strictly convex and does not really tessellate well. It's not easy. And so in particular, any construction of this type, a packing of circle with circles, it's easy to show that for almost every line, if you cut, you meet for almost every line infinitely many circles. So in particular, in this case, the perimeter is always plus infinity. Here you never have, well, let's say, okay, to 1/2, we are in dimension 2, is always plus infinity. So in this type of examples do not fall. In order to be able to pack circles with circle, you have to prescribe volume which are in some sense too big, and the total perimeter is always plus infinity because you always intersect. You have to, no, okay. There is a computation here to do, but in some sense. So, for example, in dimension 2, we have an existence result with some mild regularity, but we have not really an idea of some qualitative property of the shape. And okay, so maybe I can stop here. Thank you.
Okay, thanks a lot for the very nice talk. Now, are there questions for the talk? Can you see some questions? I don't see anybody. Sure, are you seeing? Are there some questions? I don't see.
Sure, who has the question?
Sure. Sorry.
Professor, so your method of compactness works also in the case of evolution. For example, one tries to do minimizing movements, this concentration compactness.
I don't know if so in which sense you...
For example, if you want to do GMM.
Yeah.
So this concentration compactness works. So we need uniform in time step, sort of uniform in time step, or locally uniform in time.
Yeah, well, I think if you do minimizing movement, so for example, minimizing movement for this problem, so you start from with a cluster with n equal infinity, and you just do this Almgren scheme. I don't know. Maybe, yeah, it's possible that in that case, since you penalize the distance from the original cluster, I did not think about it, but since you penalize the distance, is it possible that you can show that at each step the minimizer is not too far from the original one? I don't know. I did not think about.
No, yes. For each step you can do it. So
you are asking when you pass to the limit in the time step going to 0.
Yes.
Yeah. If you can, how do you get some compactness?
This is a bit problematic. Yes.
Yeah. Because in this case you don't have, for example, density estimates. For example, here.
Of course.
Yeah, I don't know. I don't know. Yeah.
Thank you.
Could be. Thanks.